let's begin. All right. So I was missing a very important thing yesterday when we did this one. So I actually forgot the fact that we had this data here. Okay. So we have 1.312 gram of carbon dioxide. I'm just going to go really quickly, okay? And then you have 0.805 gram of H2O. Now we divide this one by 44. Let me just bring my calculator quickly. It's still loading. Okay. All right, there it is. So just take the... This one is a bit smaller. Okay, so 1.312 divided by 44. 44 is the molar mass of carbon, okay? Carbon dioxide. So this is the number that you get. So this is about 0.03, right? So this is the number of moles of the carbon dioxide. And this one over here, so 0.805 divided by 18. 18 is the molar mass of carbon, the water. So that's equal to about that. Okay. Now that gives me this many mole of CO2 and this many mole of H2O. So from here we can calculate the number of moles of carbon, number of moles of hydrogen, number of moles of oxygen, okay? So how many moles of carbon are there, guys? That's right. So this will be, so all the carbon is in here, right? And the number of carbon dioxide is this much. So the number of carbon is the same as the number of carbon dioxide. Make sense? And the number of hydrogen is, all the hydrogen is in water, right? There are this much water, but inside of each water there is 2 hydrogens, so it must be that one times by 2, true? So times that by 2. So we get that much, which is 0.0894. 0.0894. Now we can also count how many oxygen there are. It'll be 0.0298 times by 2 because there's 2 oxygen there. Okay, and there is 1 oxygen in each water, so it must be 0.0447. So you add them up, then you get, I'm going to do that right here, 0.0298 times by 2 plus 0.04472, and you get this one, which is 0.10432. 0.10432. Now from here we found that, so what is the, let's calculate. So we can see that the ratio is 1. If we let that equal to 1 and then you divide this one by that one, this is about 3, isn't it? So that divided by that is 3. And that divided by the smallest number, let's calculate that. That divided by 0.0298, it's equal to 3.5. Okay, so the ratio is 1, 3, and 3.5. So we can easily calculate the ratio like that. Now, so the equation was carbon, hydrogen, oxygen with some number there, with some oxygen, burned to give carbon dioxide and water. And we know that because the ratio of this and this is 1 to 1.5, we worked that out yesterday. If you divide this one by itself, you get 1. If you divide that one by this one, you get 1.5. So the ratio is 2 to 3, right? Just double that. So you can just maybe put 2 there and 3 there, okay? And because the ratio here is 1, 3, 3.5, you can change that to 2, 6, 7. So, and that is consistent. 2, 6 is pretty consistent with what we have there because we have 2 carbon and we have 6 hydrogen, right? So we can go ahead and say, all right, this is 2 there and this is 6 there, right? So that's where we got up to yesterday. And we were a bit confused as to whether this was 1 and 3, then that makes it 7, right? Or it could have been, 3 and 2, because that also makes it 7. So we're not sure whether this is a 1 or 3, or it could be, there could be all sorts of possibilities, right? So that I just couldn't figure it out yesterday. And it's actually pretty simple. The total mass of this substance is 0.684, right? So this is a difficult problem. So if you don't get 100% of it, that's fine. You can just go back to the recording when your chemistry knowledge develops. You can come back and have a look at it, and it will give you a different perspective, okay? So if we just multiply, so we know that all of this carbon in the carbon dioxide came from that, and all of the hydrogen here came from that. So we just measure the weight of this and weight of that, okay? And so 0.0298 times by 12 times by the molar mass, then that weighs that much, 0.3576. 0.3576 is the weight of the carbon. Okay, so right now we're not worried about the ratios. We're just purely calculating the mass. And then you do 0.0894 times by 1. Then there are this much gram of carbon. But the total mass is this. So if you subtract the mass of the carbon and the mass of the hydrogen, then that's the mass of the oxygen, right? Yeah. So actually we didn't have to do it this way. So all we had to do was just figure out, all we had to do was just figure out this stuff. Forget about everything. So we have that much gram of carbon dioxide, so that leads to this much mole of carbon dioxide, and that much gram of the water, so you get this much mole of water, and we get the number of moles of carbon, number of moles of hydrogen, number of moles of oxygen, and we get those two. And all you have to do is just calculate the masses. I think this way is a lot easier. So you just calculate the masses. And then the total mass is how much? 0.684. And that's the mass of that guy. But then it produced that much gram of carbon and that much gram of hydrogen. So just subtract those two from it. Then that's the remaining mass that's reserved for the oxygen, right? So you get 0.237. And then you calculate the number of moles divided by 16, okay? Then you get 0.014, blah. And let's calculate the ratio of them. Then this is a 1, 3. Okay, so this is about 3, this is about 9, so it's 1, 3. And then finally divide that by 0.0298. Then that gives me 0.5. So that means the ratio is 261, right? That's why the formula is C2H6O1. Okay, so that's the end of the question. Does that all make sense to you? Yeah? So yeah, don't worry too much if this was too hard. Alright, let me just zoom out a little bit, resize. Okay, that's all good. And just draw a line there. Draw some line there. Okay, we're gonna move on to question 18. So we're just gonna finish most of the worksheet questions there by the end of 1 hour mark, so by 7:30. So we have a lot to do, so we're gonna speed up a little bit. All right, so we're gonna move on to question 18. So we talked about the limiting reagents yesterday, using the examples of, substance A, substance B, cereal, banana, apple, right? Okay, so the ratio is, so they're not concerned about the molar masses here. It's a very, very simple question they're asking. So question 1 is, how many moles of Na2S2O3 are needed to react with 0.12 mole of chlorine? So that's 4, 1, right? That's simple. You just have to do, all right. So this is you have a 0.12 mole. And how many mole of this one you need? Just have to divide by 4. Divide by 4 times by 1, right? So just have to get the 0.03. That's it. So the answer is 0.03 mole of Na2S2O3 needed to react with 0.12 mole of Cl2. That's right? So that's ratio of 1 to 4. All good? Now, I want you guys to answer B, please. How many moles of HCl can form from 0.12 mole of chlorine? The ratio is 4 to 8. Very good. The answer is 0.24. That's right. Yeah. So why is it 0.24? The reason is this is a 4, 8, so it's just double. The amount of this one is always double this one. So if you have 0.12, so then it's 0.24, just double that, okay? You can also do this technique, 0.12 divided by 4 times by 8, or you can do 0.12 times by 8 on 4, right? So it's all up to you. Now moving on to question C. Question C is how many moles of H2O are required for a reaction of this much mole of Cl2? So the ratio is 4 to 5, right? So if you have, so let me just copy the equation over here. So the ratio is 4 to 5. If this is 0.12, then how many moles of H2O? All right, so you guys can work it out. So all you have to do is 0.12 times by 5 on 4, right? Divide by 4 times by 5. That's it. So you get 0.15. Now, moving on to D, how many moles of H2O react if 0.24 of HCl produced? So, again, so that's 1, 4, 5, 2, 8. So if you have 0.24 being produced, how much water do you need? Okay. Yep, I think so. Yep. So 0.15. Yep. So all you got to do is just 0.24 divided by 8 times by 5, right? So that's equal to 0.15. Okay, so that's the end of that question. Moving on to the next question. All right. Question 19. So incandescent white of a fireworks display is caused by the reaction of phosphorus with O2 to give that. So I'm going to give you the equation. So phosphorus reacts with O2 to give P4O10. All right. So can you guys work out, can you guys balance this? It's pretty simple to balance. Yep, that's right. And the 10 oxygen there, so put 5 there, right? So that's the ratio. It's 4, 5, 1. Okay. Now right balance chemical equation, that's done. Let's move on to the next question. This stuff here. Question B. How many grams of O2 are needed to combine with 6.85 gram of phosphorus? Okay, so we got, remember the mass to mass stoichiometry? This diagram, that's mass, number of moles, mass, right? So what they're asking is, all right, you have 6.85 gram of phosphorus. What is the number of gram needed for oxygen? So you don't do that divided by that times by that. You can't do that, okay? Because that's in grams. You can only do that if it's number of moles. So first of all, you have to divide that number. Let me just bring up the periodic table. The periodic table says the phosphorus over there is 32, I think. 31, 30.974. So you got to divide that by 30.974, right? So you divide 6.85 by 30.974, then you get 0.221 moles. And then you divide by 4 and then times by 5. Do you follow everything? Times by 5 on 4. Then you get 0.2764. 0.2764 moles. And then you got to times that by how much to get the number of the mass of oxygen? Got to times by the molar mass of oxygen, right? So oxygen, I'm going to show you, oxygen is 15.999, okay? Which is 16, okay? So what should we multiply this by to go up there? Who's a little bit lost here? Anyone? You guys all okay? Sorry? Yep. So I'm just going to give you the answer, okay? Because we have a lot of things to cover. So we have 6.85 grams. Does my voice break at all? All right. So the question is, so we have 6.85 gram of phosphorus. So we divided that by the molar mass. Then we have 0.221 moles. And because the ratio is 4 to 5, we times this one by 5 on 4 to get that one, right? Now the question is, remember, how many grams of oxygen? So that's what we are looking for. Now the question is, what should we multiply by? So this is how many oxygen you have, okay? This is how much oxygen you have. And now the question is, yep. We already times by 5 here. So you know how the formula for mass is number of moles times by the molar mass. So you got to times this one by number of moles is 2764. And then you got to times by the molar mass. What's the molar mass of oxygen? But there are 2 of them. 32. So times by 32 grams per mole. See? Then you get the answer. Okay. Mihir, do you follow this all pretty well also? Okay, so you get that much as the gram. Okay. So the answer is 8.846 gram. So what we did there is mass to mass stoichiometry. So for example, if I say, all right, 4 phosphorus reacts with 5 oxygen. So if I have 5 phosphorus, how many oxygen do you need? Can you answer that question? So 4 phosphorus reacts with 5 oxygen. So if I have 5 phosphorus, how many oxygen do I need? No, you always have to divide by this and times by that, right? Well, that's right. Is that 6 really? If you do, all right, so 5 divided by 4 times by 5, right? That's equal to not quite 6, but 6.25. So that's easy to do, right? So that easy step that we have been doing, and you guys are pretty familiar with this, right? That's only at this step here. Okay? So all they told us is just the number of grams, the amount of phosphorus. So we had to convert that into how many there are, by dividing by the molar mass. And then use this technique that we used here, in here. So this is a 4 to 5. This is 0.221 to 0.2764. This is 5 to 6.5. They're all the same ratio. This is 4 to 5 ratio. This is also 4 to 5 ratio. This is also 4 to 5 ratio, believe it or not. Okay. And then using that ratio, you worked out how many oxygen there should be. And then, because we know this formula, we can work out how many grams that is. Do you guys now fully understand this question? So you have that many grams of phosphorus, and how many grams of oxygen do you need? You got to go that. Okay. So this is the mass-to-mass stoichiometry. Okay. Now, question C. Another chance for you guys to try this mass-to-mass stoichiometry. Okay. How many grams of the product are made from 8 grams of oxygen? Okay. So you guys have 8 grams. Got to convert that into number of moles. And then figure out number of moles. And then figure out number of amount of mass. All right? So you got to do, all right, the molar mass of oxygen. See, I told you yesterday that we never count the coefficient when it comes to calculating the molar mass. You gotta always calculate the molar mass of this guy, not with this one, okay? Because that number will be taken care of when you go across from one molecule to another. So this is 32 grams per mole. Now the molar mass of the P4O10, let me calculate that for you. That was 30.97 times by 4, that's the phosphorus, and then 16 times by 10. So this is equal to 283.88. 283.88 grams per mole. So I want you to use these two numbers and this formula to work out all these blank spaces there, please. Okay, so I'll give you like 3 minutes to do it. Yeah, so this must be 0.25. You got to divide by 32, right? Then you get 0.25, that's right. So you got to times it by 1 on 5. Because that's 1 there. So divide by 5 times by 1. So you divide by 5. Then you get 0.05, right? That's right, which is 283.88. That's the answer then. Okay. Yep. Mihir, did you get the same thing? 14 grams, 14.2 grams there. 14.2 grams. All right, now, next question is, how many grams of P are needed to make 7.46 gram of phosphorus? So another mass-to-mass stoichiometry. So try. So you got this one here. So that's 7.46 gram. I want to get how many grams of phosphorus is needed. Go there, and there, and then there, okay? So I'll give you some time for that. Yeah, 7.46 by 283.88. 283, that's right. Which is that 0.0263, 0.0263 moles. and then you go across, then you gotta divide by, times by 4 on 1, right? 4 on 1. Divide by 1 times by 4. Same thing. 0.105, that's right. And then you go up this way by timesing by 30.97. 3.255. So that's how you do it. So this is about the mass-to-mass stoichiometry. All good? Now moving on to the next question. All right, so we're going to try to finish all of the stoichiometry limiting reagent question there. So up to 20, 21, 22 by 7:30. Not sure if we can do that. Okay. So question 20, dilute nitric acid, so HNO3, copper metal dissolves according to the following equation. So this is the equation. How many grams of HNO3 are needed to dissolve 11.45 gram of copper? So I think you guys can try that. That's the question. So you have 11.45 gram. So you go there, and there, and there. Okay. So copper molar mass is CU right there, 63.546. 63.546. You guys just assume that H is 1, N is 14, oxygen is 16. Okay, so that's all you need. These are the molar masses. Okay, so yeah, you missed this number here, right? 3. Maybe that's the reason. All right, so let's divide this one by 63.546. So 11.45 divided by 63.546, right? Then that's the molar number of moles. So you have that many moles of that, right? And then times by 8 on 3. So times by 8 on 3. Then you get that many moles of the HNO3 needed. So if there are 3, you need 8. So what that means is that 3 copper reacts with 8 acid. You have that, yep, you have that many acid, and times that by the molar mass. Molar mass is 1 plus 14 plus 48, right? Then you get 30.27. All right. So one thing that I would like to really tell you that's important is when you do 11.45 divided by 63.546, a lot of people cut decimals here. So they go, all right, this is 0.18 approximately, so 0.18. And then in the next calculation, they just ignore all the decimals that we obtained before, and then just go 0.18 times by 8 on 3, which is equal to 0.48. But then if this was like 0.48, like 0.15, then they also like ignore all the decimals, so they cut all the decimal places there. And then they calculate, multiply that by the molar mass, which is 1 plus 14 plus 48. Then which is that one, 30.24, right? Yeah. So don't do it that way, because as soon as you cut some decimal places there, and then you use that new number, and then you multiply, and then you cut some decimal places there, and then use that new number, and then multiply, and then you cut some new decimal places there, then you'll be like losing accuracy as you go along, right? So what we need to do is 11.45 divided by 63.546, and then although you're writing 0.18 for the molar mass for this one, don't delete that number, okay? just keep all the decimal places and then carry that along with you when you do your next calculation. Okay, so that's really, really important advice for physics and chemistry students. And then you go this way, and then you have to do 8 on 3. Then that gives you all of that. So although you're writing 0.48 for your answer for this one, don't cut that all out, okay? Because that will be used in the next calculation. Multiply that by the molar mass, which is 1 plus 14 plus 48, you know? Then that's how you preserve all the accuracy, and then you just, that's why we arrive at 30.27, okay? Otherwise, you're not going to get the same decimal place, okay? So probably that's what happened with Miho, right? When you got 30.37, 31. Yeah, all right, so that's the end of question 20. And now, next question, 21. So I think this question is about the limiting reagent stuff. So 2Al and 1 Fe2O3 reacts to give 1 Al2O3 and give 2 Fe. So produces so much heat from the iron that the forms is molten. Because of this, railroads use the reaction to provide molten steel to weld steel, blah blah blah. So I don't care. Suppose that in one batch reactants, 4.2 mole of aluminium was mixed with 1.75 mole of Fe2O3. So the equation is 2Al, Fe2O3, and you get Al2O3, and then 2 Fe come out. And in some reaction, you have 4.20 of aluminium and 1.75 mole of Fe. So this is not in grams. These are the actual number of them. But this is a 2-to-1 ratio, isn't it? So if you have 4 mole, then you require 2 mole of that, right? But you have 4.2 mole, that'll require a little bit more than 2 mole, right? But you only have 1.75. So the question is, which reactant, if either, was the limiting reagent, limiting reactant? Okay. Question, is it this one or this one? This is a bit of a moment of silence. That's exactly right, yeah. Fe2O3 is the limiting one. That's the excess. That's just way too much, right? So there's a way to figure it out. So just go for, okay, scenario 1. 4.20. Then divide that one by 2 and times by 1. Then you need 2.1, right? Scenario 2, all right? Base everything off on the 1.75. Then double that. Then you get how much? 3.5, right? You don't have 2.1 because you have 1.57. You do have 3.5 out of 4.2, right? So this is what is going to happen. And that will give, because this is 1-to-1 ratio, it'll produce 1.75 mole of aluminium trioxide. And it will produce 3.5 mole of the Fe, because it's 2-1-1-2 ratio. Make sense? And therefore, out of 4.2 mole, 0.70 mole of aluminium is left. Okay? Just have to do that. So you have that, used to have that many mole, but you're going to be using that many mole, right? So the answer is, which one is the limiting reagent? It's the Fe2O3 is the limiting, and aluminium is excess. Any question? Mihar? All good? Yep, next question. Calculate the mass of iron in grams that can be formed from this mixture of reactants. So you're mixing 4.2 mole of this, not this whole thing. Don't worry about this too. All, just remember, okay, I'm keep emphasizing this. This 2, 1, 1, 2, these are, all these numbers are revealing is the way they react. Okay? 2 of this will react with 1 of that. It doesn't mean there are 2 aluminium, okay? It simply means 2 of this will react with 1 of that and will produce 1 of this and 2 of that. So this number has nothing to do with the actual number that's available. So you just have 4.2, that's how much there are. This is 1.75, that's how much there are. And to react 4.2, you need 2.1, which you don't have. To react all of 1.75, you need 3.5, you see? That's just 1 to 2, that's why it's 1.75 and this is 3.5. And yeah, that much Al is left. And that will produce that much mole and that much mole of those two. Now we need to calculate the mass of the iron that's produced. So just need to multiply 3.5 by the molar mass of iron, right? Not 2 iron. Molar mass never takes this number into account, okay? Just whatever is sitting behind the coefficient, just that one, okay? So I think the iron, if you look at this, iron is Fe 55.845. 55.845. Multiply that, then you get so 3.5 times by 55.845. 195.4, yeah, whatever that gram is, okay? That's the answer. That much gram. All good? So that's the end of that question. This was a limiting reagent question, okay? Now, what I'm going to do is I'm going to make the question a little bit more advanced. So here's the equation. Maybe I'm going to copy this equation. This equation is better. It's bigger. Alright, so I've got this here. What I'm going to say is, so they gave you how many moles there are, right? So you didn't have to go from mass to number of moles and mass number of moles. So what I'm going to do is I'm going to have 100 gram of aluminium and 100 gram of Fe2O3. Maybe that's going to be way heavier, so I'm going to make that 300 gram. And you have to figure out which one is limited, which one is excess. And the first step, of course, is to convert that into number of moles and number of moles, okay? So I'm going to give you the molar mass of aluminium. Aluminium is Al somewhere there. 26, let's say just 27, okay? So divide by 27. Fe was a 55.845. So 55.845 times by 2. There, and then plus 16 times by 3. So the molar mass of that is 159.7. Okay, so let's just say that that's 160. Okay. So 169 was it? Yeah. Then I round it down. Let me just double check. So 55.845 times by 2 plus 48, right? So that's 159 there, so 160. Yeah, 160 is correct. Was it really 169? Yeah, it'll be 159.7. But if you round it up to that, it's 160, that's right. Okay, so it'll be 100 divided by 27, then it gives you 3.7 mole, and 300 divided by 160, that gives you 1.875. So the previous question started from this level. They already gave you that and that, okay? And you had to work out which one's limited and which one's excess. Okay, so if you have 3.7, divide that by 2, because it's 2 to 1, you only need 1.85. Well, that's very close. And if you have to use all of 1.875, so it was pretty close. So I think it's I think it might give you a different result if we actually use the exact molar mass, actually, because this is so close. Yeah. So if you 1.875 times by 2, then you would need 3.75. So if this is really the case, well, let me just double check. I'm just going to use exact result because they're so close. So 26.982, 26.982. So that gives me 3.706. 706 there. And then 55.845 times by 2 plus 16 times by 3. So that's equal to that. And then 300 divided by the answer is actually 1.879. 1.879. So they're pretty damn close. Okay. So let's do it again. So what you need to do is build two scenarios, okay? So if I am to use all of this, how much do I need? 3.706 divided by 2. That's equal to 1.853. 1.853. That. And if I am to use all of it, that's really close. All of that, then it's a 1.879 times by 2. Then you get 3.75758. So which one is an impossible scenario? The first one. You don't have. Oh, yes, you do. The first one is right. The second one is impossible. You don't have that much. You only have that much, right? These are the actual amounts that you have. So cross the second part. Okay. You will end up using all of aluminium and using only 1.853 out of 1.879. Okay. So if you're given mass, then you have to first calculate the number of moles and then do this scenario. In the previous question, we just started off from this table, right? Yeah. So the question will be slightly different. It's a bit more advanced if they start off from masses. Okay. So that's it for question 21 and 22 now. We got 4 minutes, so let's do it. Minutes until 7:30. Okay. So any question from here? All good? Mihar, what'd you say? Yep, 22. I think this question is a bit similar to this one here. They start from grams, and you just have to figure out which one's limited, which one is excess. Okay. So you got silver nitrate reacts with iron chloride to give silver chloride and iron nitrate, NO3,3. Let's balance this first. I'll give you like 1 minute to try. Off you go. Yeah. So looking at the, so first AG looks, there's AG there, they're balanced. But the thing is that when you look at NO3, there's 3 NO3, right? So you would want to put 3 there, but if you put 3 there, you have to put 3 there also. But if you put 3 there, look at that one, that's 3Cl, and that matches with this one automatically, right? So I think everything is balanced in this case. So it's, yeah, that's it really. So what they're saying is that you have 18 grams and you have a 32.4 grams. You got to figure out how many moles that is, and then build 2 scenarios where this one gets used all, and second scenario is where this one gets used completely. And then figure out those numbers, and then figure out which one is excess, which one is limited. And then the question is how many grams of which reactant remains. So they're talking about which one is excess and how many moles. How many moles remain? Then you can answer how many grams remain, right? So that's what you need to do now. So I'll give you the molar mass of all of this. Okay. All right, so if you look at silver, let's take a look at silver, 107.87. So Ag is 107.87. You need nitrogen, just assume that's 14. Oxygen 16. Fe was 55.845, was it? Yep. And then the chlorine, I think that's 35.45, okay? So the molar mass of AgNO3 is, let me just calculate that. So that's 107.87 plus 14 plus 16 times 5, 3. That's 169.87. 169.87. And AgNO3, that's right. And FeCl3, what's the molar mass for that? That's a 55.845 plus 35.45 times by 3. That's equal to 160, very similar, 162.195 grams per mole. So these are the values that you might want to use. Okay. So 18 divided by 169.87, right? So that's equal to 0. Just gonna copy all of that over here. That many moles, and you do 32.4. Divide that by 162.195, right? Then you have that many moles, which is about almost 0.2. Okay, so you gotta just write that here. 0.106, and this one is 0. Just round it up to 00. Okay. So to go from there to there, 0.106 divided by 3, right? Then you get 0.0353. 0.0353. And this would be 0.6, right? Times by 3. So which one is an impossible scenario? The second one. You don't have that much. So get rid of that, okay? No need to look at it. So we will end up using all of the first one and only a tiny bit of that one, okay? Okay, so the number of moles of FeCl3 remain is how much? Just that minus that, right? It'll be 0.2 minus, we can just take the whole decimals, okay? So 0.1997595, blah, blah, blah. And then minus 0.0353, okay? Then you get 0.164, 0.164 moles remain. So number of moles of FeCl3 used is 0.0353. Anyway, so we want to know how many grams remain though, okay? So that means we need to, what's the mass of the FeCl3 remain? That's equal to 0.164 times by the molar mass, right? Which is 0.164 times by that one there. So that gives us 162.159, 26.7 gram. Okay, so that's the answer. All right. Now we're going to move on to the actual topic that you will do from next week.